The symposium is organized by Tokat Gazi Osman Pasha University from Turkey, and the symposium also is technically sponsored by IEEE Turkey section. Thank you all for your scientific contribution and support to the symposium. Dr. Figen Öktem is an associate professor in the Department of Electrical and Electronics Engineering at Middle East Technical University and principal investigator of the Signal Processing and Computational Sensing Lab. She received the BS and MS degrees in Electrical and Electronic Engineering from Bilkent University, Ankara, Turkey, respectively, and the PhD degree in Electrical and Computer Engineering from the University of Illinois at Urbana-Champaign, USA in 2014. At the university, she was selected to the list of teachers ranked as excellent by their students and was a recipient of the Professor Kung Chi Yeh Endowed Fellowship from the Department of Electrical and Computer Engineering in 2012, and a NASA Earth and Space Science Fellowship from 2012 to 2014. Before joining Middle East Technical University, she was a postdoctoral research associate at the NASA Goddard Space Flight Center, where she worked on the development of novel spectral imaging techniques for high-resolution solar imaging. Her general research area is signal and image processing, with a particular focus on the development of next-generation imaging and sensing technologies for emerging scientific and commercial application in physical and life science, and the characterization of the capabilities brought by their cyber-physical systems. Her research spans the areas of computational imaging, inverse problems, statistical signal and image processing, machine learning, compressed sensing, and optical information processing. She is a member of the IEEE and Optica. Now, dear Figen Öktem, if you want, if you are ready, you can start your presentation.
Okay. Hi, everyone. Thank you for the introduction. I will share my slides. Okay, hello again to everyone. My name is Figen Öktem. I am from Middle East Technical University. I'm a faculty here. In today's presentation, I will present you a topic that is in the intersection of computational imaging and deep learning, and how these two concepts come together to make the invisible visible. This will be a joint work. This is a joint work with my students, Okyanus Oral and Irfan Manisala, and was supported by TÜBİTAK under grant 120E505. Okay, so if we think about all the electromagnetic spectrum that surrounds us, we actually can see most of the nature or most of this large electromagnetic spectrum. Actually, what is visible to the human eye is only this little visible range from around 400 nanometer to 700 nanometer. But the electromagnetic spectrum is very large. It's from radio waves to gamma rays. There is many different radiation around us, and we cannot really see imaging at these radiation we cannot visualize this radiation with our bare eyes. And actually, computational imaging takes into the picture for that, mainly for that reason, and it makes us, it enables us to see the invisible part of the electromagnetic spectrum by using computation together with the physical systems. In my talk, I will first provide a brief introduction to computational imaging, what is it and why is it important? And then I will discuss how deep learning provides new capabilities for computational imaging. And I will provide specific examples, a specific application example from microwave imaging. Okay, let's start with computational imaging. What is it? To understand what is computational imaging, we should first discuss what is traditional imaging. Traditional imaging is actually what we learn in basic high school level science courses. It relies on the focusing principle of a single lens and the image forming property of a lens. In a traditional imaging system, we have a scene that we want to obtain an image from, and a lens. We look at the scene with a lens, and we capture the image formed by this lens or focused by this lens on the image plane using a sensor, generally a digital sensor. And with that, we get the digital image of the scene. So in the traditional imaging system, the sensor data is directly an image. And examples of these traditional imaging systems are traditional cameras, which are not in our lives that common as before. The traditional microscopes, telescopes, they were all built with this basic principle. What is computational imaging? In the computational imaging systems, digital processing or computation becomes a part of the imaging systems. So what do we mean? Again, we have a scene that we want to obtain a physical quantity related to this scene as an image. We may use an active or passive illumination on this scene. And there is a physical system, again, just like in the traditional imaging systems, but this physical system doesn't need to form an image of the scene. And actually, that might also not be possible. Using any physical component might not be able to provide you the image or provide you the image of the physical quantity of interest here. But you put here a physical system that will provide you an information or a good transformation of the image of interest. And that's what you capture with a sensor. Generally, the sensor data doesn't look like the image that you are interested in. We generally call this sensor data raw data. And this raw data need to be processed on a computer using a reconstruction algorithm to convert it to a digital image. Okay, so without this computational processing, generally we don't have an image in these computational imaging systems. So together with computation and the data, we obtain the image of interest. So in general, these are the main components of a computational imaging system: a physical system, a sensor, and a computational processing part, an algorithm basically. What are examples of computational imaging systems? Actually, I'm sure you have encountered many of them. In hospitals, they are very common. All tomographic imaging systems are computational imaging systems like MRI, CT, computed tomography, which enables to view inside the body using X-rays or other electromagnetic radiation. Millimeter wave imaging, I'm also talking about this millimeter wave imaging in more detail in my presentation. And this is also a system probably you see in airports for control. You get into the system and the radar scans through this system and provides a raw data, and then that's processed through a reconstruction algorithm, basically to see behind the clothes and to detect whether there is anything threatening like a gun or something under the body. Okay, and another radar imaging system, which is a computational imaging system, is SAR system, synthetic aperture radar. Here, for example, you see the SAR image captured from Bosphorus, Istanbul, and this is again a computational image, which is basically an image reconstructed with an algorithm. Other examples are X-ray diffraction imaging. This is, for example, this imaging concept enabled the discovery of the DNA structure, double helix DNA structure. There are also more commercial computational imaging systems like on-chip microscopy. So you can basically convert a simple phone to a very high resolution microscopy system by using an additional physical part, and by processing it with a reconstruction algorithm, computational algorithm. There are the light field cameras or augmented reality systems. There are also computational imaging systems. LightRAW is a commercially available light camera system which enables focusing any place in the scene after capturing the image. Okay. So basically, the development of next generation imaging systems mostly rely on computational imaging. With computational imaging, we can acquire new forms of visual information, which basically makes the invisible visible now, like seeing the inside the body using MRI or CT, or with microwave imaging systems, seeing under the clothes. And computational imaging also enables new functionalities like light field cameras. We can focus to any place on the scene after capturing an image, which wouldn't be possible with a regular camera. And another capability is reducing hardware complexity or cost or size using computational imaging. The example is this very small, simple microscope and very low cost microscopy system attached to a simple phone. The main steps in a computational imaging systems, it involves 3 parts. We need to first come up with a system idea. So we need to decide what physical system we're going to use here. This might involve modifying an existing design, or we can come up with a new one. And then the data provided by the system will be captured with a sensor. And then we need to perform image reconstruction using computation. And for that, we also need generally 2 things: forward problem and solving an inverse problem. In the forward problem basically means that we want to relate the observed data or the captured data by the sensor to the image of interest for the scene. Okay, so if we call the observed data Y and the image of interest, the physical quantity of interest for the scene X, we want to relate generally mathematically relate this data to the image of interest. For example, if they are linearly related, if the system is a linear system, we will have a linear relation like Y equals AX, and there can be a noise term that we can include in the forward problem. In the inverse problem, our goal is actually to perform this computational processing. We want to obtain the image of interest from the observed data. So we want to use the observed data to reconstruct the image X. Okay, so basically this corresponds to finding X such that Y, the observed data, satisfies our observation model. Okay, Y is close to A times X. And actually, we're going to discuss today that deep learning plays a significant role in solving these type of inverse problems. I'm going to provide you examples. As you might already understand, the computational imaging is an interdisciplinary field. It uses ideas or theories from many different disciplines, including estimation theory, optimization, algorithms, signal processing, physics, and such. Okay, that's a basic introduction to computational imaging. Now I wanna explain how deep learning is used recently for computational imaging systems. So as I said, for the image reconstruction task in a computational imaging system, we need to solve an inverse problem. Inverse problem is basically the opposite of the forward problem. In the forward problem, we relate the data to, or we relate the output of the system to the input of the system. But in the inverse problem, we want to reconstruct or infer the input of the system by using the output of the system. Okay, so given basically the goal in an inverse problem is given the noisy data y, and if possible, the forward model or the system model y equals x, we want to estimate the desired image x. Okay. In general, inverse problems are much harder to solve compared to forward problems. You can easily understand this through the simple puzzle example. If we ask you to sum all the numbers along the columns, along the rows, or for all colors and such, this is a very simple task, but this is a forward problem task, and even a primary school student can solve this one. But the inverse problem equivalent of this puzzle is now giving the column sums, row sums, and color sums of these numbers and trying to infer these numbers. And this is, of course, not a trivial task. So in general, inverse problems are more difficult than forward problems. If you think in the computational imaging context, generally the available data captured through the physical system is a discrete data. It's finite, it's noisy, it's generally limited or undersampled. And another difficulty is forward model, the observation model, y equals ax. Equation generally has errors, and these two together makes it very difficult to obtain a solution for the inverse problem. Actually, an exact and a unique solution almost never exists in any inverse problem, practical inverse problem. If we think of using simple inverse or city inverse or least square solutions, generally these are not useful in the computational imaging context because they suffer from non-uniqueness issues, large errors due to instability or noise amplification issues, and such. Okay, what are the common approaches to solve inverse problems? Basically, we can talk about two different types of algorithms, traditional algorithms not based on deep learning. The traditional direct inversion methods, these actually try to solve directly the unknown image x from the data y using an analytical relation. They basically, by using the forward model relation between them, you are trying to analytically invert this equation and obtain x equals something in terms of y. Okay, so this is generally possible for many imaging systems, and it provides a fast, non-iterative algorithm, generally easy to compute, but it provides very poor performance with noisy and limited data because it ignores the discreteness of the data, the noise on the data, and it doesn't exploit any prior information about the image of interest. The more commonly used methods are regularized reconstruction methods or regularization-based methods. In these methods, we incorporate additional prior information about the image of interest that we want to infer, such as sparsity, into the inversion or reconstruction process. This is generally done by using a maximum posterior estimation approach and using a regularization term in addition to a data delta term, and solving an optimization problem. A common framework is compressed sensing frameworks. In compressed sensing frameworks, we always use regularized reconstruction, basically sparsity-based reconstruction. Compressed sensing actually tells us that images can be recovered from far fewer measurements than the traditional methods use. For example, if you look at the image here, let's say it has like 200 by 200 pixels. To represent this image, we don't need this 200 by 200 pixels. If you, for example, take its wavelet transform, look at the wavelet coefficients, you're going to see that there are actually very few significant wavelet coefficients in its representation. And if you only keep these large wavelet coefficients and just set the others 0, by only storing these wavelet coefficients, you can still get a very good representation of this image, which is here. Okay, so which tells you that you can actually represent this image, or you can obtain this image from very few measurements compared to its original size. But yeah, to benefit from the sparsity idea, sparse representation idea in a transform domain, generally we need to solve a convex optimization problem. It will involve a least scarce term plus a regularization term that will involve L1 norm. And this will enforce sparsity in a transform domain. Here, T will be a sparsity-inducing transform. So like wavelet transform here, when we take the wavelet transform, this image has a sparse representation. But generally, the question is how we should choose this transform. Of course, it depends on what type of images you're interested in. Like, are you interested in natural images, or are you interested in like organ type images, or other like images with particular structure? Okay, depending on this prior information, you need to choose a good sparsity-inducing transformation. So prior knowledge is of course necessary to choose this transformation, but even when you do that, that transformation can be a good one for some of the images, but not maybe for all of them. It might not be very convenient for all the data or for all the image that family of images you are interested in. So actually deep learning comes into the picture at this point. And it provides reconstruction techniques that enables new capabilities. And the way we use deep learning for solving inverse problems can be also categorized in the same way we have for the traditional methods, direct inversion and regularized reconstruction. Now we use deep learning to perform direct inversion, or we use deep learning to perform regularized reconstruction. How do we do that? For learning-based direct inversion, we basically train a neural network to learn the inverse mapping from the available data Y to the desired image X. Okay, so we expect the neural network to perform this inverse mapping task directly. Or in the learning-based regularized reconstruction methods, we train a neural network to learn the type of images we are looking for or we are interested in. So that actually means we want to learn the prior information from our available training data, and we want to use it in our regularization when solving the inverse problem. So that actually enables us to replace the handcrafted analytical priors in our regularized methods, like the ones that involve L1 norm, with data-driven deep priors. And I'm going to talk about both of these two example methods, how they are applied in a sample application. These are going to be results from our research group. So we're going to consider a microwave imaging setting. What is microwave imaging? Microwave imaging is a radar imaging technique that forms three-dimensional reflectivity image of a scene from the measured radar data. This is, remember, the airport control system. This microwave imaging systems are used in airports for control purpose. For example, you can see a hidden gun by using a microwave imaging system, by scanning this person with a microwave imaging system. This actually has a wide range of applications, from airport security to concealed weapon detection, true wall imaging, medicine, and such. To explain you how we exploit deep learning for this microwave imaging setting, I need to briefly explain you the inverse problem. So as we said, the goal in the inverse problem is to reconstruct the unknown three-dimensional reflective distribution of the scene, which I'm going to call as S, from the available radar measurements, which I'm going to call as Y. We can, by using Born approximation, we can see that there's a linear relation between Y and S through a matrix, and that matrix will contain these complex exponential terms, which will depend on the distances between transmitter and the voxel of interest in the image, and the distance between the receiver and the voxel of interest. Basically here, we have a MIMO array system, a multiple input, multiple output array system, and a transmitter sends a radar pulse to the image, to the scene of interest, and this radar pulse is reflected back, and that's captured by a receiver, receive antenna, and we get many radar measurements by using different transmitter and receiver pairs, and we use that data Y to reconstruct the reflectivity distribution, which is actually complex on the scene. Okay, so I'm going to provide you a learned direct inversion example. So in this one, we want to directly go from our complex valued radar measurements to the desired three-dimensional reflectivity image using only neural networks. So here, in the first stage, we use a fully connected layer because the dimensions of the measurements and the desired three-dimensional image are not the same. So and this is also complex valued, we can concatenate this real and imaginary parts and provide as input to the fully connected layer. And that will provide an intermediate three-dimensional reconstruction for the image. And this will be input to a three-dimensional neural network, which will provide refinement, which will perform refinement on this intermediate reconstruction to get the final reconstruction. Okay, so this is a fully neural network-based approach. I'm gonna show you how it performs. An alternative one to this one is physics-based learned direct inversion approach. In the first stage here, we use a physical relation, or we use the forward model, exploit the forward model. How do we do that? We map the complex valued measurements to an intermediate 3D reconstruction by using the adjoint or the Hermitian of the system matrix. So we simply multiply the measurements with a Hermitian, and that's an analytical computation step, and then we perform a refinement with a three-dimensional neural network to get the final reconstruction. The three-dimensional neural network we use is a three-dimensional unit architecture, which has multi-resolution capability, so it works at different scales. It learns the models the image at different scales, starting from this size, and it goes until this size. Okay, that's the second method. The third method, I wanna tell you how regularized reconstruction, how we include deep learning to regularize reconstruction. For any regularization, we need to take into account prior information. Here, our prior information is this one. We know that scene reflective the values have random phase, and they are they have locally correlated magnitude. Because of this, we wanna enforce regularization only on the magnitude because phase is random. So we wanna enforce a regularization function on the magnitude of the reflectivity values S. And we want to also satisfy our observation model with a small error. Okay, this is a small error because we know that there is noise on the data, so we don't expect to satisfy the forward model relation exactly. And basically, we formulate this optimization problem, and to solve this optimization problem, our solution approach involves variable splitting, ADMM, and deep prior. ADMM is an optimization approach, augmented direction method of multipliers, and is commonly used for efficient solution of inverse problems. In the interest of time, I cannot go into details of the derivation of this ADMM steps, but when you apply variable splitting to this problem and then apply the ADMM steps, you're going to come up with 3 different steps. 2 of these are analytical computations, so you can easily compute that. And the third one is a denoising problem. So you need to solve a denoising problem here in this update step. And that's actually where we're gonna benefit from deep learning. First, actually, you can see that this denoising problem, you can show that this denoising problem can be solved by simply performing denoising only on the magnitude of the input and keeping the phase as it is, and then merging this unprocessed phase with the denoised magnitude. Okay, so that corresponds to solving this denoising problem. This, of course, requires a proof, but that's what we did. To benefit from deep learning, we're going to replace the denoiser here with a deep denoiser, because deep learning is a very good tool to solve denoising problems, and we're going to benefit from its power on this denoising problems, and we're going to use a deep learning-based denoiser at this stage. And for this, again, we are going to use a 3-dimensional deep denoiser as before. Okay, I'm going to quickly show you how these 3 different methods performs in an application. So I'm again considering the micro imaging application. We have an antenna array here, 2-dimensional Mills-Cross antenna array. It contains 13 transmitter antennas, 12 receiver antennas, and it works in an operative frequency from 4 to 16 gigahertz. And we wanna, using this antenna array, we wanna image the scene of interest that is here. So basically a distance of 0.35 meters from the antenna array. Okay, and here are some results with simulated data. So if this is your ground truth, your ideal reflectivity image that you want to obtain, if you use traditional direct inversion method, that's what you're going to get. As you see, it has a very bad performance. The noise is amplified everywhere, and the ground truth is buried in artifacts and noise. But if you perform learning-based direct inversion, which is purely neural network based, that's also still not very good, because for a neural network, it's generally a very difficult task to learn the inverse mapping from a complex valid data to a 3-dimensional image. But if you use the physics-based learn direct inversion approach, where in the first stage we benefit from an analytical computation, and then we use a neural network processing for refinement, that actually performs quite well. When we look at the regularization approaches, if we use analytical regularization, like sparsity-based regularization, this is what we're going to get. But if we perform learning-based regularization, as I explained, by using a deep learning-based denoiser, this is what we're going to get. And this is actually the best one in all of these methods. So learning-based regularization generally provides the best capability, but it generally has the drawback that it has longer computation time compared to the other learning-based methods. So this is also this also shows the average performance on the test data set that contains 100 different images. And on the average, again, the learning-based regularization method is the best one, but it is slower compared to the direct inversion methods. But it's still much faster compared to analytical regularization methods. Here is also an example, a result with experimental data, real radar data. There's a scene that contains a toy revolver that is basically metal, and a spiral mime array is used to get radar data from the scene, which was 50 centimeters away from the toy revolver. Again, here you see the traditional direct inversion result and physics-based learned direct inversion results, which is much better than this one, and the analytical regularization method and deep learning-based regularization method. As you see, like both of them outperforms their traditional counterparts, and their learning-based regularization really provides all the details of this revolver. Okay, with this, I can conclude. Basically, I briefly told you that the joint design of imaging systems and algorithms plays an important role for the development of next generation imaging systems. And on the algorithm part, deep learning plays an important role for data-driven reconstruction. We can learn the prior, or we can learn the inverse mapping from the available training data. And this generally this type of methods generally outperforms their conventional counterparts. Here are some relevant recent publications about these works. And with that, I can finish my talk. Thank you for your interest.
Thanks for your presentation, dear participant. Do you have any question about the study? Okay, no question.
No, I have a question.
Okay, please.
So
You can ask.
previously, yes, as this reconstruction of images from sensor data, actually I studied this in my master 20 years ago with spline methods. I guess this traditional direct inversion, maybe these spline methods, I guess we did some interpolations. I don't know, am I wrong, but do you think also these splines could be applied here? Of course, this is the data driven. We have more data now, and we don't need to use some linear methods, maybe.
Here, a simple interpolation is not possible because you have a complex valued radar data and a three-dimensional ground truth object. There is no interpolation relation between them, but there is an analytical relation between them, which is called as back projection. So it's a very well-known method in the microwave imaging community. So if you want to directly invert your data to obtain the image, so the exact analytical expression is given by back projection sum. Okay, and that's here what we use. So any other method will not perform better than this one, because this is the exact relation.
Yes, it's back propagation is this Newton methods for you get gradient, I guess.
No, this is not back propagation, back projection method.
Back projection.
Yeah.
Okay. Thank you very much.
You're welcome. Thank you.
Okay. Are there any other questions, dear participants? Okay, no question. Dear Figen Öktem, thank you for your attending. Thank you for your presentation.
Thanks for the invitation.
Very much for accepting our invitation. Very valuable information you have provided also. I wish you continued success in your career.
Thank you for the invitation. You're welcome. Have a good conference. I wish everyone a good conference.
Okay, thank you. Yes, dear participants, the last session of the symposium, the first special session of the symposium is over. The next session will start at 11:15. I want to ending the special session. I wish you good days.
Thank you. Bye-bye.
Thank you.